Okay, so before I continue, is there any question from last time? Anything you want to ask? No? Good. So we ended up last time discussing, discussed how to measure entanglement for bipartite pure states, right? And this is what I want to continue now. So it'll be about, again, and later we go to mixed states, but and let me introduce this measure of entanglement that last time we already saw it, entropy of entanglement, so what we call it. I'll denote it by E. Q state psi is just the phonomenon entropy that we saw last time of any of the two reductions because they're the same. So rho A is the reduced state of psi, and this is the same as S rho B. So that's the definition. Okay, so as before, right? So let's see some extreme examples. If psi is a product state, then if you trace out B, A is still pure, is a pure state, and therefore the entropy is zero. So there is zero entanglement, as it should be, right? Now suppose that psi is a maximally entangled state that we wrote last time, like this, this superposition of perfect correlations between A and B. If you trace out B, then we have the maximally mixed state on A, right? And therefore the entropy is the maximum value possible. If it's a d-dimensional system, if it's a d by d dimensional entangled state, the entropy is log d. So for qubits, the entropy varies between, for 2-qubit state, is between 0 and 1, right? Okay. So I'm going to show you that, in a precise sense, this is the unique measure. So that's the only measure that matters in the asymptotic limit when you have many copies of the state. So there is a very easy way to describe the theory in that setting using this quantity. So you play a fundamental role. But before that, let me start here. Okay, so let me start with that and then we go back. So let's study now state transformation. What is the idea here? The idea is that suppose we have a quantum state, rho AB, for example, but it's shared by Alice and Bob, and again, we are in this distance lab paradigm, so they can only implement LHC. But now they would like to transform this state, the quantum system described by this state, into a different one, right? So, by applying some LHC operation, they would like to go to another state, let's call it sigma. And the problem I want to address is to find conditions for this transition to be possible, right? When this transition is possible. Note that it's not always possible, right? So what is one example where this cannot be done? Suppose rho AB is separable and sigma AB is some entangled state, like the maximum entangled state, right? Then we saw last time that LC maps separable to separable, so there is no way you can do this transformation. So definitely there is some pair of states for which they are not connected by LHC, but we'd like to understand this better. And a setting that I want to consider is what we call the that's probably Tim ahead. And this is a situation where we don't have just one copy of the state, but we have a large number of copies of the same state, right? So suppose now we want to understand if we start with n copies of the state for a very large n, when can we go to n copies of C or maybe some different number of copies, m copies by LHC. And again, to simplify things more, it's okay if we just go to some approximation of this guy. So maybe we don't exactly get sigma, but we get some state which is close enough to sigma in some way that we're going to quantify. And then we're going to understand the setting. Okay, so why we want to understand the setting? Well, one motivation is just that it gives simpler answers. So you see, we could address just the single, is what I call a single shot one, when you only have one copy. But usually this gives some complicated answers, or sometimes you cannot even solve the problem. In this asymptotic setting, it simplifies things a lot, right? So just think about some kind of thermodynamic limits if you want. Okay, and we understand that when n and m are much bigger than 1. All right. And now I want to consider this question for pure states. Okay, and then I'll give you the answer. I'll tell you a complete solution to this. Okay, so like given any two pure states and n here, what is the m that you can have here, the largest m, such that it's possible to do the transform, right? And you see it's related to that, this one here. Okay. So to do that, I will consider two particular processes, two-state transformations. One is a process we call entanglement distillation. And what we want to do here, we start from some states. Rho A B again, the same thing. And we want to understand, if you apply some elasticity process, what is the largest number of copies that you can get from a 2-qubit maximum entangled state, right? One of these EPR pairs. So we start with n copies of rho. We end up with n times ed copies of phi plus. This is what we call the distillable entanglement. Okay. So what is the mathematical expression for that? We want to take the maximum, but minus this, or like supremum, but think as a maximum over all r, which is like a rate, such that when n grows, when the number of copies grows, if we look at how close we minimize over all quantum operations lambda n, which is LOCT. Okay, so might appear really complicated, but let me just break it out to you. So this is this is called trace norm. I'll write the definition now, but it's a measure of distinguishability of two quantum states. So here we have two quantum states. One is a LHC operation lambda n applied to n copies of our state rho. Okay. And the output of this, we want it to be close to n times r, right? This is this r here, copies of a APR pair, right? Of this maximum entangled space. And then there can be some small error. We allow some small error, but we want that in the limits, when n grows, when n goes to infinity, the error goes to 0, which means, right, this trace norm, the limits here being 0, right? So we can use any elasticity we want. We optimize over process, right? So we wanna extract the CPR pairs in the best way possible. So that's why we minimize over all LCCs, this difference. And R is just the maximum number for which we can do that, right? So if you choose a R very big here, then this limit might not be 0, right? So then we decrease R is still not 0. At some R, this limit starts being 0, and that's the optimal R that we want. And this is this measure, right? It's distillable entanglement. Yes. I will explain the significance now. But yeah, thanks for the question. Any other question? Yes. Because like for each n, uh, you might choose a different LSTC process, right? So you fix the number of copies and then you optimize over the best LSTC operation for that number of copies, right? And then you try to get as close as possible to n times r copies of phi. But then you increase to n plus 1, and then you can choose a different LSTC here, right? Well, it's true that the limit might not be well defined, but it's I mean, I'm assuming the limit exists, right? So this expression here, this minimum here, is a function of n, right? Let's call fn, right? And it's a function of n that I'm requiring that goes to 0 when n grows, right? It's kind of I'm saying, yeah, I'm required there is a limit here. Okay, so you can think of the syllable entanglement maybe as like the most relevant entanglement measure, right? Because it tells us the usefulness of the quantum state if you want to do teleportation, for example, right? Suppose you want to use the state for teleportation, and later we see quantum key distribution. We can also do if we have this EPR pair, right? So that's a state of like perfect or maximum entangled. So it's a useful state. But sometimes Alice and Bob, they have some, because of right, their system are noisy and they have initially some rho AP. So maybe they want to distribute entanglement and they send through one pass through some optical fiber, but there is loss. And in the end, they only share the state rho AB. And they can do that many times, so they can establish many copies of this rho AB. But it's a noisy state. So then what they can do, they invest a large number of copies of rho AB, and they extract a small number of copies, but now of a better quality entangled state, right? This maximum entangled state. And then they can use for applications, right? They can use for teleportation, for example, if they want, or something else. Okay. You can define the same quantity with separate operations, yes. It's not as operationally meaningful, right? But we do not know how to. Oh, okay. So for pure state, it would give the same expression. I will be able to have a closed formula expression for this. I can already tell you the entropy of entanglement, but we'll see that later. But for mixed states, in general, we do not know how to compute it. This is like a very hard problem. Okay, even for 2-qubit states, we do not know how to compute it in general. Actually, only for a very special case, we know how to compute. So it's a very interesting quantity, but it's very hard to handle. Which is one of the reasons why we consider so many other entanglement measures as like some maybe approximations to this one. But for now, I just wanted that the definition is clear. So if it's not, let me know. Before that, let me just review what is the trace norm and why we use it. Right, there was a question. So the trace norm of some operator x, then we compute to take the trace of the square root of x bigger x. Okay. Now, if we specialize for 2 density matrices, which is the case that we want, there is a different way of writing it, which is meaningful. You can write it as 2 times the maximum over all m, which is smaller than identity and bigger than 0. So what is this? M is just a P of M element, right? Of trace m rho minus 6. Absolutely. Okay. So what is this? This is just the bias that you can get if you want to distinguish rho from sigma, if you can use any measurement allowed by quantum mechanics, right? So in a problem where you want to distinguish rho and sigma, the best way, the best protocol for distinguishing rho and sigma, it has some probability of success, right? So let me write P success. And this is equal to half. Half is like if you flip a coin. So like half is if you cannot distinguish them at all, you can still say, okay, I always think I have one of them, and then plus half the trace norm difference of the two. Okay. So if the trace norm is the maximum value, which is 2, you can perfectly distinguish them. If the trace norm is 0, you cannot distinguish them at all. Not more than like with a fair point. And if in particular the trace norm is small, it means that for all practical purpose, they are really the same state, right? You can only distinguish them if you do one experiment in one and the same experiment in the other one. You only see some difference up to the spectra of epsilon, right? So for a small epsilon, that you can ignore that, and that's why we use it. Okay, it has this very clear operational meaning here. Which was your question? Okay. Yes. Yes. Or you can change the dimension, yes. And it's important to change, right? Because like the idea is that you start from this entangled state, but which is like noisy. So the amount of entanglement per copy is small, right? And you want to concentrate it, right? So you want to distill it into a pure form, but with less copies, right? Yeah. Yes. Yeah. This means that that this guy is a 12 copy of M, right? So it means that you can, right? So if you want to distinguish two quantum states using the best measure, the most general measure quantum mechanics, what you can do, you do a 12 copy of M, right? And if you get this, you say they have rho. If you have this, you say you have sigma, right? So this just really gives the, right, because of the way of writing like that. This is like a result, right? You can prove that's defined like that. You can also rewrite this way. I won't show you, but it's not hard. But then, right, it just gives the optimal, it's just related to the bias of optimal distinguish the rho from sigma by any measurement in quantum mechanics, allowing quantum mechanics. Yes. Um, 1/4, why? Because it's like, right, that's the expression, and this is the bias, right? Um, I don't see it, but okay, let me, maybe you're right, so maybe it's a 4 here. Uh, okay, let's go back to that later, just because I don't have it. But okay. All right, so that's one definition. Now I wanna, yes. Oh, yes. This here, yeah, you maximize. So, oh, okay. This is, sorry, maybe it was the way. This absolute value trace m times rho minus sigma. Okay, so it's just the trace of the product of m times rho minus sigma, and you maximize over all m. M is just an operator, it's a Hermitian matrix, which all eigenvalues are smaller than 1, and they are all positive, which makes m a P of m element. Right. So what I'm claiming is that defining like that, you can rewrite the trace norm in this case where it's a difference of two quantum states like this. So this is like try to prove it, but it's a true result. Yeah. I didn't tell you how to do it, but it's yeah. Um, if you want, you could just define the trace. Forget about this definition. Just think we define like that, and that's why we want to use right this expression. But okay. All right. So no, I said this entanglement distillation is really right a useful primitive in quantum computing. If you want to do quantum, if you want to distribute entanglement over a large distance, you have to do it on a quantum repeater, for example, right, or and so on. Now we wanna look at the reverse process, which maybe is not so useful. Is like entanglement. Uh, Dilution. So now we want to start with some good state, like EPR state, like a perfect and a maximum entangled state, and just dilute it into a larger number of copies potentially of a more noisy state. Okay. Why we like to do that? It's not clear, but can still define, right? Uh, so what we want to do now, we want to start from uh, a right expression, but this is like in the diagram. So we start from some number of copies of the maximum entangled state, 2-qubit maximum entangled state, and biology we map to n copies of rho AB. And the number of copies that you need of the maximum entanglement state per copy of your final state is what we call the entanglement cost. Okay, it's this ET function. So what is the expression? Is very similar to that one, right? So EC will be equal to the supreme over R of the limit when n goes to infinity of the minimum over LCC so exactly as before, right? So we want to start with n times R copies of the APR pair. We apply the best LCC possible to get as close as possible to our target state rho AB, n copies of it. We want that in the limit when n grows, it becomes perfect, the approximation. The error becomes 0, and we look at the maximum possible, right? So wait. This should be. We look at the minimum number of copies that we need, the minimum R, such that this is possible, right? Yes. Well, that's why I put supreme and infinite, right? Because then I don't have to know, right? So if I put minimum and maximum, there will be a problem, right? Because perhaps it's not attainable, right? But the infinite supreme will take care of that. Then that's okay, because then the Hilbert space is fixed, and it's true, because LCC is not closed, not yet. Thank you. It's correct. Yes. There is some analogies with thermodynamics in this process that we're seeing. So you could think as some kind of free energy as where although it's like I guess the Silo Bentame is more like a free energy, right? Because it tells you the free energy tells you how much work you can extract from the state, right? And then if you think of work as, for example, how many qubits you can teleport, right? Then that's exactly the Silo Bentame, right? That's a different process, right? Where it's like this is like the amount of work that it takes for you to construct some particular system, right? To form the system. There is reversibility in thermodynamics and ideal conditions, so this is actually the same there, right? And you see they are also the same here in some particular case, but not in general. But we see that. But yeah, people like these analogies of thermodynamics, and there are papers written about this and so on. Yes. It's not clear. It could be that indeed there are many optimal LCC protocols here. Yes. Okay. Great. So with that, let me introduce you one of, in my opinion, as I said before, most interesting results in quantum information. It's a result by Bennett, Brastar, Schumacher, Wouters, Mullin, Popescu. So what they show that the entanglement thought for bipartite Q state is equal to the scale of entanglement, which is equal to the entanglement, the entropy of entanglement. Okay. So in that case, really, if you are happy with asymptotic transformation, everything you have to know about entanglement is encoded here in this unique, or in this like single value function, right? Which is, it's kind of. I'll show you actually how to prove it now, and you see once you think about it, it's not so hard to prove it. But if you see at first, kind of remarkable result, right? So we have this very complicated expression involving like have to take minimums over LCC, which is already this complicated class that I mentioned before, right? You take limits even. Like a large on LCC X on a large number of copies, and in the end you get such a nice result, right? So that's one of the points of considering this like this is called IID setting, where you have many copies of the same states, and this asymptotic limit is because you have a hope of getting nice solutions like this. Not always it works, but here for example it works. Okay, so some notes here on this result. first, as I said, E is an entropy of entanglement. You completely specify state transformations. Right? And tell you what this is. But another way to say that, sometimes this expression is used. The theory is reversible. So what do I mean? So suppose we start from some psi, n copies of it, okay, and then we can go to we can do entanglement distillation, and we can go to phi plus n e psi copies of it, right? Because the distillable entanglement equals to it, right? But we also know the reverse process, right? So we could also do the dilution process here. So we can start with n times the entanglement cost, number of copies of phi, and get n copies of psi. But the entanglement cost equals to the distillable entanglement. So this is kind of reverse, right? We can go back and forth here, right? So with n copies of psi, we can convert into n e copies of n e psi copies of phi, back and forth, right? So in cases like we don't lose anything. And then what we can go to another state, right? We can do the same process, but now going to some state phi. And then what we get here, we get the ratio of the entropies of entanglement, right? So what this is saying is that all this, every bipartite free state is really, in what concerns its entanglement property, in the sense of you have LCC for free. You can trade one for the other as long as you match the number of copies of them, right? So all that matters is this function here. So n times e psi copies, right? So you can go from any state to any other as long as you match the amount of entanglement in them, right? So they can have different amounts of entanglement measured by this, but then you compensate by that by going to a fewer number of copies of the other, right? So just to write in a different way, with n copies of psi, very large n, you can go to m copies of phi, and vice versa, the reverse process as well, as long as n times e psi, which is the total amount of entanglements in this n copies of psi, right, equals m times e phi. Okay. Yes. Sorry. No, because then in that case, this will be 0, right? That's right, because LCC, you're allowed to change the dimension, right? In LCC, you can throw things out. You can do any local operation you want, right? For an operation. So this includes, yeah, you can add an oscilla, you can remove an oscilla, you can make a local measurement, right? You can trace out parts of the system. Yeah. So indeed, it's very important you can change the dimension here. Yeah. If n is not infinity, indeed, people work out well, it's like single shot, but even like some scaling where n is large but not so large, and then there's some corrections. So then this quantity is the most important one, of linear term. Then there is another one which kind of sets the square root n behavior, and some kind of variance of this function of the entropy. And then this third order is like log n. There is another expression for that. So this is understood. But even more, you can ask, okay, suppose I only have one copy, right? If something like this works, and then it doesn't work anymore. There is not only one complete function. There is a family of functions, and this connects to the theory of majorization, which is also interesting. So again, we completely understand the case of one copy here, but we have to look at majorization, which is something that I won't cover. But it's you can check it if you want. It's also a nice answer. Okay. Yes. Yeah, no, this is because I was not very careful. So the correct definition would be to put a ceiling here on n times r, or a floor, doesn't matter. And the same there. Indeed, you have to round up to the nearest integer. Okay, so let's show it, right? So I wanna show this to you, how we get it. And to do it, we will take a little bit of a detour from entanglement. Sorry, for the next 20 minutes. And let's analyze another interesting problem in quantum information, which is compression. Okay, so you see that this is very connected to compression. And let's look at compression of classical sources first, just like Shannon compression. And let's review how it works. Okay, so let's consider the following problem. Suppose you have a string of letters. Well, sorry, string. Yeah, of letters. With alphabet. Okay, so we have one of the possible k symbols, a1, ak. So this is what we call alphabet, just the number of possible different elements. So for a binary alphabet, it would be either 0 or 1, right? But it can be a larger alphabet. So that's how you do. And Gaussian simplification, kind of similar to these many copies of the same state we had there, is that we will consider the I the limit, or sorry, the I the regime, which is when we assume each of these letters is drawn independently and identically distributed from the same distribution. Okay, so this is independent and identically distributed regime. So each letter occur with probability p ax. And we assume we have long message. So we have like a message with n letters, where n is much larger than 1. And the question is now, suppose we want to transmit this message. Okay, Alice wants to transmit to Bob. You can just send a message uncompressed. This takes n times log k bits, right? The alphabetic k. For binary alphabet, take n bits. But can we do something better? And because of this assumption, the assumption, we will see that we can. That we can compress to a shorter length, which will be related to the entropy of the distribution, right? So that's one of most important results in information theory due to Shannon a long time ago. So let's see how it works. So the question we want to ask is whether we can compress. Okay. All classical for now, yeah. Later we'll try to do the same thing for quantum states, but now, yeah. So, okay, first, let's look at the binary alphabet. So suppose 0 appears with probability 1 minus p, and 1 occurs with probability p. So by the law of large large numbers, right? So for typical strings, so I mean like with very high probability you get a string with some particular property. This we call typical strings. There we have roughly n times 1 minus p zeros and n times p ones there, right? So n is very large, so we expect each time we get 0 probability 1 minus p. So right, so because we have many independent samples from the same distribution, we expect that the empirical average or the empirical value of the number of zeros approaches really the expectation value, right, which is n minus 1 minus p for zeros and n p for ones, right? Of course, the order of 0 and 1, we don't know anything about it. It can be any order, but right, no, with very high probability, the string that we get will have this number of 1s and 0s. Okay. How about the number of these strings with np1s? How many do we have? Well, again, so we fix the number of ones there, but they can appear in any location. So the number of such strings is given by n plus np, right? All right. And now let's just get a nice expression for this. So let's just use Stirling's approximation here and try to rewrite that binomial in a different way. So let's look at the log of n and p. That's the log of n factorial, np factorial, and 1p factorial. And let's use Stirling's approximation, right, to each one of them. So this is the same as n is roughly to leading order n log n minus n minus np log np minus n times p plus n1 minus p minus n1 minus p. Okay. So I just use, well, right. This expression. And then if you simplify things, you find it that this is equal to n times the Shannon entropy of p, right? Where this is just the binary entropy, h of p, is minus is the basically the entropy of the binary distribution you had before. Okay, so just a subtlety here, but I will leave to that. Note that this is the number of strings when you have exactly n times p1, right? And of course, what will happen is that most of the strings will have roughly n times p, right? 1, but there will be some variation, right? But some variation of order like square root n here, and therefore the number of typical strings is like this binomial coefficient where you have np, but also when you have np plus 1, np plus 2, and so on, right? But the point is that there aren't so many of them, so I'll just treat one of them as a good approximation for the total, for this sum. Okay. So the number of typical strings will be roughly write this factorial, which we just saw is 2 to the n HP. Okay. So if we would do this more correctly, where we vary from NP just to some many numbers like centered around NP, but with some variation, we have to sum a bunch of expressions of this form. But there is like really just polynomially in n many of them. So this does not change the exponent here. So that's, but I'll leave to you to think about it. Okay, so what is the idea of compression? Now it's simple, what we should do. So let's specify typical sequences by a binary string of length n times entropy of the distribution. Okay. So what will happen? So we have this set of strings of this number of them. We can assign a label of n times HP bits to each one of them, right? And then this is the information that we're going to send. So we just transmit the label of the typical string, okay? And this we can do just communicate this number of bits, right? So before we had to communicate n bits, now we have to communicate n times the entropy of p bits. So unless this is maximum, unless this is 1, then there is a compression, there is a saving here. But how about the atypical sequence, right? How about these unlikely sequences which are not depth to anything here? Then we just, for example, say abort. So just say, okay, in that case, there is an error in the protocol. And the point, law of large numbers tells us that when n grows, the probability of getting an atypical string goes to 0, right? Another way of doing it is like variable length. Whenever we get an atypical sequence, we just send it uncompressed. And then, right, not always we send n times entropy of p bits. Sometimes we send a little bit, we send more. But the probability that we send more is very small, right? So like the expected value of the message is still this order. So there are like choices they can do here. But that's the message, right? The message that the entropy tells us how much compression we can do, right? So what you can show is that the probability that you get a typical string decreases exponentially with n. Say again? Yeah, no, but note that the messages, they do not have uniform probability of appearing, right? Because the distribution is not uniform, right? So, you know, it has to be more careful, but that's it decreases exponentially in n. Anyway, okay, so you can, let me see time. Maybe, you know, you can do the same thing for a larger alphabet, like with K, and if you do that, you get the entropy, the Shannon entropy for, right, whatever distribution you have. Very similar derivation, but because I don't have so much time, I'll skip that. So, so let me not tell you how to do it. Sure. So, well, it depends on the level of detail, but suppose, right, you have this alphabet as the one. So, and right, and we have the probability distribution P AX, then can compress the message, right, to n times h of p bits, where this h of p is the Shannon entropy. which has this expression. Okay, and it'll be the same, so you can define typical sequence in the same way. But what will be a typical sequence now? A typical sequence is a sequence where the A1 label appears roughly PA1 times N times. The A2 symbol appears roughly N times PA2 times, and so on. Right? And we can show that with very high probability to have a typical sequence, and we can show that the number of these typical sequences is exactly 2 times N, but now this entropy. Okay, so it's pretty similar. All right. So now let's go to the quantum case. Yes. Then you can, it's called like single shot information theory. You can define expressions that look like entropy. They call like, for example, in that case, the answer would be what is called a max entropy. But it's also, Graham, for example, would say that you haven't solved the problem because it's kind of a redefinition of the problem. So it's hard in that case, Yeah. So I would say that you can get nice answers if you have some structure there. It doesn't have to be ID, but some structure. For example, if you have a Markov chain, for example, then there are nice ways to express entropy in terms of some more illuminating than just this max entropy. But in the completely structureless case, yeah, you do not have a very nice answer, which makes sense, right? Because then what kind of code you can do? We live right to, yeah, you just have to send your message, uncompressed sometimes. Right? Okay, any other question? All right, so let's see this quantum case. What is the problem we have here? Okay, remember, in the classic case, we had a source spitting out these letters according to the same distribution over and over again, right? Now we have something, we want something similar in the quantum case. What would be the analog? It's just that we have, prepare, for example, electron in the same quantum state over and over again. So in the end, after we have n electrons in the same quantum states, we have rho to the power of n, right? So that's our source, our quantum source. And suppose this is a d-dimensional state. Okay, so rho is a density matrix on CD. Then how much and how we count like storage, right? We wanna count the amount of stuff that we have to send or that we have to store. Well, we count by the dimension, right? And by the number of qubits, which is the log of dimension. So to store this guy, the dimensional state, in the worst case, it takes n copies of it. This takes n log d qubits to store, right? But now the idea is, can we do something better? Can we store in a smaller number of qubits? So how you can think about that? You can think that you can apply an encoding map. E, what is that? That's a quantum operation. It's a trace preserving completely positive map. And we map this to some sigma n, okay? Then this is, you put in the memory if you want, or you send this from Alice to Bob if you want. But then there should be also a decoding bit, which allows you to get another state rho n, which is a very good approximation of your initial state, okay? And the goal is to minimize the dimension of this guy, okay? So we want to make the, we want to take the minimum of the dimension over sigma n here. The smallest dimension of this guy here in the middle, the better, right? The more compression you have. And now what we want to understand is what are the limits, right? So what is the smallest dimension we can get here? Or it's better to talk in terms of qubits. What is the minimum number of qubits that we need here to be able to do this? And we will see, not surprised, the answer will be the polynomial entropy of the state. Okay, so that's, this is also called Schumacher compression sometimes, because Ben Schumacher, he figured this out a long time ago. Okay, so what is the idea? The idea is to go to the eigenbasis of rho, and once you go to the eigenbasis of rho, right? This probability distribution given by the eigenvalues of rho is there, and basically we can do just the classical coding to this probability distribution, okay? And that will work, and that's the point. But let me show you the details. Yes. Well, no, there's no entanglement here at the moment now, right? So that's like well, I'm confused, but there's no how you want to introduce entanglement to this problem. This is like this works for a single particle now, right? There's no entanglement yet. Maybe what you want to say is that you want to map it to the maximum mixed state of the smallest dimension possible, right? Which is kind of correct. You won't be exactly maximum mixed, but it's kind of true. We map it to a state which is like, in a sense, close to a maximum mixed state in the smallest subspace. So that's true. Yeah. What you're saying, I think, is correct. Once we look at the entanglement problem, it will be something like this indeed. We'll map to some smaller maximum entangled state, and that will be the entanglement distillation part. But we'll see that later. Yeah. Okay, so we have row n. It has some eigenvalue decomposition, right? This is the some eigen decomposition. We take it n folds. Right, that's the state that we get in the end. We just expand this tensor product here. And now remember we had the typical strings before, right? And they were the key concept that we needed. It's just the strings that appear with high probability, right? And then we only care about them in a sense. Here we're going to do something similar, but because it's quantum state, let's define a notion of a typical projector. Okay, so this will be a projector, P. I don't know by P typical. And what we're going to do, we are going to sum over all strings which are typical strings for the probability distribution P. Okay, so this will be over x1, xn. Typical. I'll define what typical is next, but you already know what it is intuitively from there. And then we do sum. So we say that's x1 typical if that the case. Okay, so delta, just think of delta as some small parameter. Can be even a sequence going to 0, but so what is a typical sequence? It's just a sequence for which the probability of getting it, right, roughly 2 to the minus entropy, right? Which, you know, it's 2 to the n times the entropy, which is what we saw there. So what you can show is that the probability of being typical is overwhelming, right? And almost all sequences will be typical when n grows. And this we're just projecting, right? The projector onto all strings, right? But now as quantum states, which are typical. Okay. What is the key? Let's look now at the probability. Suppose we just measure this projection versus the orthogonal projection on the state row. Then let's just see that with very high probability we will get the p typical. That's the overlap of rho n with p typical is very high. Okay. This delta is like this delta is just a small parameter that we fix it at first. So we choose what I'm saying here works for every delta. It doesn't matter how small it is. Because I glossed it over. It should also be there. But, yeah. Yes. Yes. Yeah. So this is the eigenbasis, right? We don't have to know rho for compression. That's universal compression. Yes, I'm assuming we know rho. Here, I'm assuming we know which basis we can. Okay. So, sorry. Well, no, because you can do this universal compression, but it's more complicated, and I want to do it very. I don't have an easy way. Do you know an easy way of doing universal compression? Right. Yeah. So that's why. If you know, it's much simpler because then you can. Yeah. Otherwise. Yeah. Yes. Yes, that's right. So, I mean, each one of these guys is one of the eigenstates of rho, right? So, in this typical string would be, sorry, would be I. It's the thing. I'm just labeling right the eigenstates by I, and then you can think as a string. But right, indeed, this is like this is not like the computational base or anything, right? This labels the eigenstates of rho, right? That's simple. Yes. Yeah, this is just log px1 up to times pxn. It's just the total probability of measuring of seeing the string. I changed to I. I1, I2, In. Right. But because it's id, the probability of seeing this string I1, I2 up to In breaks down into the product of p I1 times p I2 times p I3, and so on. Yes. 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 Okay. There is. Well, maybe I already said this now, but then you can say, well, if he already knows, then what is the point, right? So this could be 0, right? Because D can just create the state itself, right? But the point is that we don't want D to know the state. So we allow E to know rho now, but we don't want D. Another way I'm more interested in saying that is that this is a mixed state. This mixed state can be entangled with some reference. I want the compression preserves the entanglement with the reference. Okay, so that's important. We'll get that, but I will not show in the table. But I'll go back to this comment later. Well, let me just show you some calculations. So, where I was, let's look at trace p typical rho power n. What is this? This is just the sum over all strings which are typical, right? Is the probability is just the probability of getting a typical sequence, right? Which we know goes to 1 when n grows, right? So when n becomes larger and larger, this p projects more and more into rho, right? So like really the most of the weight of rho is in this subspace, p typical, right? Okay. On the other hand, what is the rank of p typical? well, that's the number of typical sequences, right? That we saw before is smaller than 2 to the n times entropy of P. And now if you don't want to be, well, let me use that. Right, roughly, at least to leading order. But what is the entropy of P? Entropy of P is the entropy of the eigenvalues of rho, right? Which is the von Neumann entropy of rho. Right? So this is 2 to the n von Neumann entropy of rho. Okay. Right. So now, what is our encoding map? E is the encoding map, like that I defined there. So is a quantum operation. What it does, you can write like this. So first you sandwich X with P typical. So basically you measure the P typical, and if you get there, yes. What do you mean classically encode the eigenvalues? Yeah. I yes, but then this would violate this assumption that I made that the decoding D should not depend on the states, right? Because then you would need this information about the eigenstates to recover the state, right? Which I don't want something like that. And I'll tell you why I don't want something like that soon, which is to preserve the entanglement with the purification. So that's but let me get to that. So what you're saying is true, but then you wouldn't yeah, then we say it's true, but then basically you compress the classical information, and that can basically know already anyway, so you can just reconstruct it right in the end, which is not what we want to do. Okay. So, and why this setting makes sense, right? Maybe it's a bit contrived now saying this can depend on rho, but this shouldn't, because think about this communication setting. So maybe Alice has this guy and wants to send it to Bob. So maybe Alice knows the eigenbasis here, but Bob doesn't know, right? So she can do the encoding knowing what rho is, get the compressed version, send to Bob, but Bob doesn't know rho, so he should be able to decode, doesn't matter, right? What he gets. Okay. So what is this encoding? You measure if you're in the typical subspace. If you are great, then that's what happens to the states, right? If you measure the orthogonal complement, if you measure that you're not there, you throw away the states and prepare whatever. You prepare the zero states. So that's a channel. It's a valid quantum operation, right? You can check. Strength preserved, completely positive. Everything is good. And what is the result? Because of this property, you can show that the encoding applied to rho n is very close in trace norm, for example, from rho to the power of n. Okay. I don't want to go in detail, but that's true. Think about it yourself. Now, is this doing compression? Well, let's see that it is, because let's look at the range of E applied to rho n. So what is this range? Is the dimension of P typical, right, of the subspace plus 1, because maybe this is not in P typical, right? But what is the dimension of P typical? It's here, right? So it's 2 to the n f rho. So what it shows, we can encode now, or can store if you want, in n times s rho qubits. Okay. So that's how it works. What would be the decoding in that case? Well, the decoding would be to do nothing, right? So you don't have to do anything. So there is really this decoding. You could consider it in general, but you don't have to, right? This encoding already gives some good approximation of rho, right? That you can just use if you want. Or maybe the encoding really is just you have to map this guy which still lives in this n copies of a log d-dimensional system to a space of qubits of that form. That's just a mapping of bases, right? So you just map the two bases of the two spaces. And then the decoding will be just the reverse thing. But there is nothing active there, right? So it's just the way you label the bases, if you want. Okay. Now, one thing that we will use, but I will not prove that is the case, but it is the case, and that's why compression is an important thing in the quantum case, is the following. Let me just draw a picture. Yes. Maximally mixed states, right? In that case. Yes, indeed. It's the same thing as class. If you start with a maximally mixed state, you cannot do any compression. Yes. Exactly. Yeah, right, because that's a valid quantum operation, right? So this means like the way to think about this operation physically is that you have a projective measurement with two operators. One is p-typical, the other is identity minus p-typical. You measure it. If you get p-typical, you accept. So that's the post-measurement state there, right? If you get the other one, then you throw away the state you had, and you prepare the zero state, right? So that's how you can implement this. And why it's important to throw away? Well, because you want to have something of very small dimension here, right? In order to, right, for compression to be effective. All right. So, okay. Right. So I had this row, right? Then we were doing compression. Now, and now let's put S system. Now, any such row, right? You can look at the purification, what we call purification, which is a pure state now of S and E, okay, such that trace with respect to E of psi SE equals rho S. Okay, so mixed states, you can say, okay, they are the more general objects in quantum mechanics, representing a quantum state. It's true, but in a sense, also you can say that psi is the fundamental object, in the sense that every density matrix row, every mixed state, actually comes from a pure state where we do not have access to the whole state. Right? So that's what the concept of a purification. Now you can say, okay, so maybe I wanna do compression in the system S as we did before, but preserving the purification as well, right? So what is the idea here? The idea is that we have psi, right? Fe, so S and E, and we have many copies as before. Let's do like E and S. And now here we want to do the compression. Okay, here we want to apply this encoding operation. Excuse me. So you want to apply this encoding operation, map this to a small number of qubits, maybe communicate with something else. But not only you like to preserve the reduced density matrix here, the state rho here as before, we would like to preserve the global states. Okay, we like to preserve the purification. And it turns out, and it's not hard to show, but I don't have time to show you. But it's true. This encoding does this as well. Okay, so quantum compression also preserves. Then I will say that is a preserved the entanglement with the purifying system. Okay, so even though this is like a reference, we don't have access to it. It stays there the same. But if you apply this encoding operation here, in the end, you still have a state, a pure state, which is for which here you can store in a small number of qubits, and overall it's still close to the original pure state on S and E. Okay. Yes. You mean how you implement? Depends on the basis that you have, right? But it's so. You mean like physically on a physical system? There is explanation. Yes, yes. Oh, you're talking about the complexity of implementing it. So So suppose a binary it's actually not complicated to measure. Suppose a binary alphabet, just for simplicity first, okay? So what it means to be typical? It means that a binary alphabet and then the eigenvalue is like p and 1 minus p, right? So with very large n, it means that you want to roughly have n times p zeros there and 1 minus p n ones there, right? So so basically you want to fix the Hamming distance, right, of your strings there, right? But only that. You only want to measure the Hamming distance and nothing more. So how you can do that? In that case, you can just measure the total sigma z operator, right? You just measure the total magnetization in the z direction, okay? You measure this observable, but only this observable, and then you say, okay, I want to get the outcome of roughly np plus minus square root n, right? And then the post-measurement state will be exactly implement this fixing, right? So how you do that with a large alphabet? It's more complicated, but it's something similar, right? So you just fix like I want to have like P1 ones there and P2 twos there and P3 threes there and so on, right? P1 times n and P1 there. So it's not a complicated measurement in the end, right? Okay. You can think like that, but you can also quantify closing like trace norm or closing. There is another measure called fidelity, which also works. So yeah. So you can do the Schmidt decomposition, and now you're saying you want to truncate the like atypical one Schmidt decomposition. Yeah, that will work. That will introduce some small error. You're right that if the error was epsilon trace norm, now it might be 2 times square root of epsilon. So you lose a little bit, but not too much. You lose something that is independent of the dimension. But exactly doing this conversion from the density matrix to this Schmidt decomposition, right? Where, yeah. But I know I didn't. This is just yeah. I didn't give you a lot of details here. Okay, so now let me go back to this entanglement thing and show you one part of the results. So let's show how compression, quantum compression, like directly implies that you can do entanglement dilution as the cost given by the entropy of entanglement. Oh, about your question, I glossed over, right? Because what I said is true. Yeah, 0 and 1. If it should be not in the z direction, it should be in the direction of the eigenbase of your Hamiltonian, right? In other words, you apply the rotation from the eigenstate to the computational basis, and then you implement this Z measurement that I said, right? Okay. So let's see the proof. EC psi b. Let's show that it's always smaller than its psi, than the entropy of entanglement. Okay. So how it works? Alice locally prepares n copies of psi. Maybe okay, or some registers a and a prime of her. So she has that. Then she applies compression, Schumacher compression or quantum compression to the a prime subsystem, right? So to a1, a and n. Okay. And she sends the compressed information and sends to both. Well, not send, sorry. And she teleports the state to Bob using the entanglement, right? So she cannot send qubits, right? But she has entanglement. She can use entanglement and send classical communication, right? Teleport compressed state to both. Okay, so first, by what I explained there, right, in words of compression, this will work in the sense that in the end they will share the right states, right? So in the end they will have psi AB to the power of n, right? Why? Well, because compression doesn't change the state too much, right? Now, what is the cost? So what is the number of EPR pairs? So they need one EPR pair per qubit that is teleported from Alice to Bob. What is the number of qubits? The number of qubits by compression is n times entropy, right, of rho b, right? Because that's the entropy of the reduced state here of psi, which is n times the entropy of entanglement. Right? So, this shows that, right? I just show you a protocol for which using n times entropy of entanglement psi copies of EPR pairs, number of EPR pairs, can prepare n copies of psi. Right? Maybe there is a better protocol, but you see that there isn't. I'll show the other direction in the end once we combine, the dissimilar entanglement result as well. Okay, so that's one direction, really just compression, right? So, what is the classical communication cost here? Who knows how many classical bits they did this protocol? Twice, right? So teleportation for each qubit, you need 2 classical bits. So the classical cost is 2 times n entropy of entanglement. There are more economical ways of doing that. The best protocol uses the square root n classical bits, and that's necessary. Cannot do better than that. It's more subtle. I don't tell you what to do, but that's okay. Because teleportation for each qubit that is teleported, you need to send 2 classical bits, right? Remember teleportation, right? There was this one of 4 Pauli operators that you had to communicate, right? Which one, right? So teleportation teleports, sends the information up to this unitary on Bob that has to be undone, right? And he has to know which one, and it's one of 4 possibilities. Okay. So let me show you now. Let me see the time. I have a little bit. So at least it's not hard now once we have this prepared. This direction. Then we can always distill at a rate given by the entropy of entanglement. And let me do it. First, let me show you for 2 qubits now, okay? For now. So suppose psi. Let's write in the Schmidt decomposition, and then we can write it as right. That's the states in the Schmidt decomposition. Know that we can always think we can always map the Schmidt decomposition to the computational base if you want. This can be the computational base, because by LCC we allow any local unitary for free, right? And because it's local unitary, the local change of basis doesn't cost us anything, right? So we can map any 2 qubit states to something of this form by LCC. Reversibly, right? Which then we don't lose anything. Okay, great. Now we have n copies of this. So that's the say we have. And now by LCC, we would like to seal, the maximum number of copies of the phi plus state as possible. So the maximum number of EPR pairs possible. And now we will look at exactly this measurement that you asked. So this measurement will be used here. So Alice. She just performs a local measurement. on her n qubits of the total spin along the z direction. So what is the observable that she measures? Is just a sum of sigma z for each one of the n spin half particles that she has. So yes. Well, they are the same, but this proof only shows that it's smaller because I just gave a protocol for entanglement dilution at that rate E, right? But you could say maybe there is a better protocol, right? It turns out that there isn't, but no, we're going to see that soon, right? But so far, I just show you a protocol which achieves this E, right? So yeah, I didn't show you there's optimal, but it turns out that it is. All right, so she measures sigma z total for this guy is sum I1 to n sigma z I. And note, what I mean to measure this guy, it's a subtle measurement, right? It's just not to compute the expectation value of this guy. It's really a measurement in the quantum space. We look at the eigendecomposition of this guy, has all these big projects with these big degeneracies, right? And we want to project in one of these blocks, right? So it's very important to keep the coherence inside the degenerate subspace, right? So in other words, what we're doing, as I mentioned before, Alice is measuring the Hamming weights of of her parts of the states, right, of the strings that she has. Or the Hamming distance. So right, because she has it's perfect correlation between Alice and Bob. So whatever Alice has, Bob has as well. Once we decompose this guy, this tensor power, we will see that there is all this sequence of the typical things have roughly p n1 and 1 max p 0 there, and they're all over the place. So so in the expression of this psi n, there are n plus m terms in superposition, right? So note now it's some superposition with Hamming distance m. So let's just suppose that we make this measurement and we get some particular m. So we project onto this subspace of Hamming distance m. What is the post-measurement state, right? So that's the important thing. Sorry? From 0. Yeah, so the Hamming weights, actually. Yeah, indeed. So post-measurement state. It's uniform superposition of all n plus m terms. Yes. Yes. So actually, have called Hamming weights, but let's call it Hamming distance too. It's just the number of ones that there is on the string. So what is this post-measurement state? Well, up to a change of basis, right? So we can write it as I1 T. This I just labels all possible elements of Hamming distance M. Okay, now. So maybe I could call it different. Yeah. But now this is on Alice. And note, Bob didn't do anything, but Bob is perfectly correlated, right? So Bob has the same thing. and here we divide by 1 over square root of d, and d is n choose m, right? So the post-measurement state, after we get these results, is a maximum entangled state of dimension given by this n choose m, right, that we got, okay? Now, I will show you this next time, but what you can show is that with very high probability, as it happens, right, when we are analyzing the compression problem, this thing here will be equal to 2 times n, the entropy, right, the entropy of entanglement, right, the entropy of the source, which is the entropy of entanglement. And that's why you get in the end, this entanglement delay. So you just like basically measure into a particular type. This is like a, well, there is some name. I don't want to get into that, but basically you just do this simple measurement into the Hamming weight, and then once you get the Hamming weight, you automatically are projecting onto a maximum entangled state of some smaller dimensional space, but with very high probability, the dimension will be roughly the dimension of n times entropy of entanglement EPR pairs, right? So we'll go back to this next time. Let me stop here. That's it. Thanks.